On September 15, 2017, a spacecraft traveling at nearly 111,000 kilometers per hour sent its final transmission as it plunged into Saturn's upper atmosphere. Engineers expected the signal to disappear within moments, but what they didn't expect was that the final stream of data would challenge decades of assumptions about the planet they had spent more than a generation studying. Buried within those last measurements was something far more valuable than a dramatic farewell. They revealed a region of Saturn that refused to behave the way every accepted scientific model predicted, forcing researchers to reconsider ideas they had trusted for almost 30 years. Was an evidence of alien life or some mysterious transmission from deep space? In many ways, it was even more fascinating than that. The instruments aboard Cassini recorded conditions that simply weren't supposed to exist, according to the best planetary physics available at the time. Several years later, after scientists carefully examined every packet of information returned during those final seconds, one conclusion kept appearing again and again in peer-reviewed research. The observations were extremely difficult to explain using any known physical process. That phrase carries enormous weight when it comes from experts who have dedicated their careers to studying Saturn. It doesn't mean the measurements were unreliable or that something supernatural had occurred. It means the spacecraft functioned exactly as intended. The data was clean, the instruments were perfectly calibrated, and yet reality refused to match the models scientists believed were accurate. That is what makes Cassini's final chapter so extraordinary. This is not the story that usually appears in headlines. Most summaries simply explain that Cassini ended its mission by diving into Saturn to avoid contaminating one of its potentially habitable moons. While that is technically true, it leaves out the discoveries that continue to reshape planetary science nearly a decade later. The real story begins with those final months, when mission planners decided to send Cassini somewhere no spacecraft had ever dared to travel before. Those risky maneuvers produced measurements that researchers are still trying to understand today. And every new analysis seems to raise even more questions instead of providing comfortable answers. To understand why those discoveries surprised everyone, we have to go back to the beginning of Cassini's remarkable journey. After leaving Earth in October 1997, Cassini spent almost 7 years crossing the solar system, before finally arriving at Saturn in July 2004. It became the first spacecraft ever designed to remain in orbit around the ringed giant, opening a completely new era of exploration that scientists had dreamed about for decades. Over the next 13 years, Cassini transformed Saturn from a distant world into a place of astonishing complexity. It completed nearly 300 orbits, flew past Titan more than 100 times, skimmed the icy moon Enceladus dozens of times, transmitted hundreds of thousands of photographs along with millions of scientific measurements back to Earth. Every year seemed to bring another discovery that no one had anticipated. Cassini revealed towering storms stretching thousands of kilometers across Saturn's atmosphere. It watched gigantic hurricanes circle the poles, mapped the intricate structure of the planet's rings in unprecedented detail, and discovered that tiny Enceladus was spraying enormous plumes of water into space from an ocean hidden beneath its frozen crust. By almost any scientific standard, the mission had already exceeded every expectation long before it entered its final phase. After more than a decade in orbit, however, a difficult problem emerged. Cassini's fuel reserves were running dangerously low. Without enough propellant to maintain precise control of the spacecraft, NASA faced a serious dilemma. If they simply abandoned the probe, its orbit would eventually become unstable, creating a small but unacceptable possibility that it could crash into Enceladus or Titan sometime in the distant future. That possibility deeply concerned planetary scientists. Both Enceladus and Titan had become some of the most promising places in the solar system to search for environments capable of supporting life. Even though Cassini had been sterilized before launch, no one could guarantee that microscopic organisms from Earth hadn't survived somewhere aboard the spacecraft. Allowing the mission to end naturally could contaminate worlds that future generations might one day explore in search of alien biology. NASA chose a different ending. Instead of letting Cassini drift uncontrollably through the Saturn system, engineers designed one final series of daring maneuvers known as the Grand Finale. The spacecraft would repeatedly dive through an unexplored gap between Saturn's atmosphere and the inner edge of its rings before deliberately sacrificing itself inside the planet.
Wait!
It was an extraordinary decision. For 13 years, mission planners had carefully avoided that narrow corridor because nobody truly understood what was waiting there. Computer models suggested the region might be filled with countless tiny fragments of ice and rock moving at enormous speeds. Even particles only a few millimeters across could destroy a spacecraft traveling at orbital velocity. To reduce the risk, engineers pointed Cassini's massive high-gain antenna directly into its flight path during the first dive, turning it into an improvised shield against whatever debris might be hiding ahead. Everyone expected impacts. Many scientists believed the spacecraft would emerge peppered with microscopic damage after each crossing. Instead, something completely unexpected happened. The impacts never came. When Cassini transmitted its measurements back to Earth, researchers were astonished to discover that the supposedly dangerous gap was almost empty. The particle detectors recorded far fewer collisions than predicted, and the environment appeared dramatically cleaner than every computer simulation had suggested. This wasn't just a small disagreement between theory and observation. The difference was so significant that scientists immediately realized something fundamental about Saturn's inner ring system had been misunderstood. According to existing models, countless particles should have been drifting into the gap from the surrounding rings. Instead, the region remained surprisingly clear, almost as if an invisible process was continuously sweeping material away before it could accumulate. No one had predicted that. Even today, researchers continue investigating what mechanism keeps this narrow region so remarkably free of debris. Some believe Saturn's powerful magnetic field may be removing electrically charged dust particles. Others suspect subtle gravitational interactions within the rings themselves. So far, no explanation fully accounts for what Cassini observed. And that was only the first surprise. The next discovery would prove even more difficult to explain. The real surprise emerged only after Cassini switched on one of its most sensitive scientific instruments during those daring dives. As the spacecraft skimmed through the narrow space separating Saturn's atmosphere from its rings, its ion and neutral mass spectrometer began sampling the sparse gas and microscopic particles surrounding the probe. Scientists expected the instrument to detect mostly water molecules and tiny fragments of ice drifting inward from the rings. Instead, the readings revealed a chemical mixture far more complicated than anyone had imagined. Hidden within that thin veil of material were large organic molecules, compounds significantly more complex than simple methane or carbon dioxide. These weren't the kinds of molecules researchers expected to find floating freely in such a hostile environment, exposed to intense radiation and near vacuum conditions that should have broken them apart long before Cassini ever encountered them. The discovery immediately raised a difficult question. If these complex molecules weren't supposed to survive there, where had they come from? Planetary chemists quickly began testing every explanation they could think of. Perhaps sunlight interacting with frozen material inside Saturn's rings was slowly producing increasingly complicated compounds over millions of years. Perhaps collisions between icy particles were triggering unexpected chemical reactions. But every model encountered the same problem. The chemistry simply wasn't producing enough complexity to match what Cassini had actually measured. The spacecraft wasn't reporting a small anomaly that could be dismissed as measurement uncertainty. It was detecting a chemical inventory that existing theories struggled to reproduce. That is why several scientific papers describing the discovery used unusually cautious language. Rather than claiming a breakthrough, researchers admitted that the observations were not easily explained by any currently understood mechanism. For scientists, that sentence is incredibly important. Science advances whenever observations disagree with theory. The data itself wasn't controversial. What became controversial was the realization that the accepted explanation for Saturn's inner environment was probably incomplete. Even stranger was the composition of the material itself. Cassini detected not only water vapor and organic compounds, but also incredibly fine silica nanoparticles suspended within the region. On Earth, silica forms the basis of common rocks, sand, and quartz. Finding particles this small near Saturn suggested that some kind of energetic grinding process was continuously breaking larger materials into microscopic fragments. Researchers believe countless collisions between icy ring particles slowly pulverize material into dust over enormous spans of time. Yet once again, the numbers refused to cooperate. The amount of silica Cassini measured was significantly higher than theoretical erosion models predicted. Something appeared to be producing or transporting these particles much more efficiently than anyone had expected. Together, the organics, water, and silica painted an entirely new picture of Saturn's rings. Rather than acting like passive bands of frozen ice circling the planet, the rings appeared to behave as an active chemical laboratory. Sunlight, radiation, gravity, and constant collisions were transforming the material in ways scientists were only beginning to understand. This also changed the way researchers thought about a phenomenon known as ring rain. For years, astronomers suspected that material from Saturn's rings slowly drifted downward into the planet's atmosphere. The idea was supported by indirect observations, but nobody had ever measured the process directly. Cassini finally did. As it repeatedly crossed the gap during the grand finale, the spacecraft recorded streams of water, dust, organic material, and charged particles flowing from the rings into Saturn's upper atmosphere. It was the first direct confirmation that ring rain was real, but the measurements revealed something nobody anticipated. The flow wasn't uniform. Some regions delivered enormous amounts of material, while others remained comparatively quiet. Certain latitudes experienced much heavier infall than neighboring regions, suggesting invisible magnetic and electrical forces were guiding particles towards specific locations on the planet. The rings weren't simply falling apart under gravity. They were interacting with Saturn's magnetic environment in an incredibly dynamic and complex way. Every new orbit seemed to replace one mystery with another. Instead of confirming existing theories, Cassini's final months forced scientists to rewrite many of them from scratch. What had begun as a carefully planned farewell mission was rapidly becoming one of the most scientifically productive phases of the spacecraft's entire 13-year journey. And then came perhaps the most astonishing discovery of all. It wasn't hidden in Saturn's rings. It wasn't buried inside its atmosphere. It came from the planet's magnetic field, for finding so unexpected that it challenged one of the fundamental principles scientists use to explain how planets generate magnetism in the first place. Every major planet in our solar system generates a magnetic field through the movement of electrically conducting material deep inside its interior. On Earth, molten iron circulating around the core creates the invisible magnetic shield that protects life from harmful solar radiation. On the gas giants, the process is different, but the underlying physics follows the same fundamental principles. Deep beneath Saturn's cloud tops, hydrogen exists under pressures so immense that it behaves like a liquid metal, conducting electricity much like copper does on Earth. As this metallic hydrogen circulates through the planet's interior, it generates Saturn's enormous magnetic field, extending millions of kilometers into surrounding space. For decades, scientists believed they understood how planetary magnetic fields worked. Although every planet produces its own unique magnetic signature, one feature always seemed unavoidable. The magnetic axis should be tilted, at least slightly, relative to the planet's rotational axis. Earth's magnetic poles are offset by roughly 11 degrees, while Jupiter's magnetic field is tilted by nearly 10 degrees. Even the ice giants Uranus and Neptune possess dramatically tilted magnetic fields, creating strange and asymmetrical magnetic environments. Saturn, however, refused to follow those rules. Before Cassini arrived, astronomers already knew Saturn's magnetic field appeared unusually well aligned with the planet's rotation. The alignment was surprisingly close, but the available measurements still allowed enough uncertainty for scientists to believe the tiny offset would eventually become visible with better instruments. Cassini changed that assumption forever. During the grand finale, the spacecraft repeatedly flew closer to Saturn than any probe ever had before. Those close passes allowed its magnetometer to measure the planet's magnetic field with unprecedented precision, eliminating many of the uncertainties that had existed for decades. When researchers finished analyzing the data, they were stunned. Instead of revealing a small magnetic tilt, Cassini showed that Saturn's magnetic field was aligned almost perfectly with its axis of rotation. The difference was measured at less than 1/100th of a degree, making Saturn's magnetic field the most perfectly symmetrical ever observed on a planet. That result created an immediate scientific problem. According to the mathematical framework used to explain planetary dynamos, a perfectly symmetrical magnetic field shouldn't be able to sustain itself over billions of years. Tiny instabilities should naturally develop inside the flowing conductive material, producing at least a slight tilt. Saturn wasn't supposed to look like this. The measurements were repeated countless times, verified from different orbital positions, and carefully checked for instrument errors. Every independent analysis reached essentially the same conclusion. The spacecraft wasn't wrong. Theories were incomplete. Planetary physicists suddenly found themselves confronting one of the biggest unresolved puzzles in modern space science. Either Saturn possesses an internal structure unlike any planet previously studied, or some entirely unknown process is organizing its magnetic field into an almost impossible level of symmetry. Neither explanation has been confirmed. Some researchers suggest that a hidden layer of electrically conducting fluid deep inside Saturn may be suppressing the normal magnetic instabilities. Others believe differential rotation within the planet somehow smooths out magnetic irregularities before they can grow large enough to become detectable.